Welcome to our second video lecture. In this session, we're going to talk about molecular orbital theory, the corresponding materials that you should cover in the text is in chapter 5.1 all the way to chapter 5.4. The overall objectives are the following. First of all, be able to understand the basic concepts of molecular orbital theory and be able to sketch MO diagrams for diatomic molecules. Those are specifically our first and second row homonuclear and heteronuclear diatomic molecules. In addition to that, be able to read and understand MO diagrams of polynuclear molecules. Now, the construction of those polynuclear molecules MO diagram is pretty complex because it involves some of the symmetry and point group concepts that we did not cover in this class. So the requirements one level lower. I do not expect you to sketch a MO diagram, but simply be able to read and understand the diagram that is presented to you. And finally, be able to use the MO diagram to predict molecular properties such as bond order, bond length, and what would happen if you impose some changes to a molecule. All right, first of all, let's quickly go through the basic concepts of MO theory. Now, the MO theory is very different from the Lewis dot structure or the hybridization orbital theory that you are probably more familiar with. The basic ideas here are the following. First of all, in a molecule, electrons stay in so-called molecular orbitals. Now, those molecular orbitals are made from linear combination of atomic orbitals. Now, those atomic orbitals would be the ones that are associated with each of the atoms that make up the molecule. Okay. Now, in a Lewis dot structure, the idea of a bond is localized, meaning that when there's a bond, it is formed by electron sharing of two atoms. Okay, and what that means is the bond is localized between two atoms. Now, in the MO theory, things are different because electrons are in the so-called molecular orbitals, and the molecular orbitals are not necessarily confined between two atoms. Instead, it can primarily localize on one atom, or maybe two, or maybe three, and could even be all over the place. Okay. Now, this is an important difference between the Lewis dot structure and the MO theory. Now, the next important thing is how you're going to construct a molecular orbital. This is important because you will need to understand this so that you can sketch a molecular orbital diagram. Now, there are three criteria that we look at. The first one is that the symmetry of the atomic orbitals must match each other. Okay. Their symmetries may not necessarily be exactly the same, but there has to be some symmetry matching properties. Otherwise, they cannot form molecular orbitals. And second is that the atomic orbitals must be spatially close to each other so that they can have effective interaction. Okay. Now, this one is similar to the Lewis dot structure concept in that if two orbitals are really far away, they cannot overlap, so they cannot form a bond. The third one is different from the is different and new. It basically says that those two atomic orbitals must have similar energies to have effective interaction. Okay. Now, once you have the molecular orbitals constructed, what you do then is to fill up all the electrons associated with the corresponding atoms and fill those electrons into the molecular orbitals. And when you fill the electrons, you use the similar rules we talk about in atomic structure discussion. Okay, so basically you start from the bottom to up. You want to maximize spin. You should never have two electrons having the same set of quantum numbers. Okay, so basically all the same kind of rules we talk about when discussing electron filling in atoms. All right, so now we're gonna look at one example and talk about how a molecular orbital diagram is constructed. Okay, so here is oxygen, and oxygen has 6 valence shell electrons. And in the Lewis dot structure, which is shown on the left, it formed 2 covalent bonds to make the whole to make both oxygen atoms happy. That means by sharing 2 electrons to form 2 bonds, both oxygen would have 8 electrons in their valence shell. So that's the structure of O2 in the conventional Lewis dot structure interpretation. On the right hand side is the molecular orbital diagram. Now there are many different things here, so I want to break them apart. Now on the left and the right are cartoons. Those are the cartoons of the molecular orbital. Okay. Now in the very middle, those are the molecular orbitals that are produced by linear combination of atomic orbitals. Okay. Now on the left and the right, you'll find a lot of lines, and those lines indicate the energy level of the atomic orbitals. You'll find there are labels of 1s, 2s, and 2p. Okay. And you'll find dotted lines connecting the atomic orbitals and the molecular orbitals. Okay, so basically what you have is on the left you have one oxygen atom, and on the right you have another oxygen atom, and the atomic orbitals of the 2 oxygen atoms that have the same symmetry will interact, and if their energies are close to each other, then their interaction will be more effective. If their energies are far away from each other, then the interaction will be less effective. Okay. And on top of that, there's also a spatial overlap requirement, meaning that if 2 orbitals are close to each other, then their interaction will be stronger. Okay. Now, keep those 3 things in mind. We can look at how the molecular orbitals are produced. Okay. So first of all, you can look at 1s and 1s. Okay. Now these 2 orbitals interact with each other, form 2 molecular orbitals. They're labeled as sigma G and sigma U star. Okay. And the sigma indicates the kind of bond that is produced, basically a sigma type. We're going to talk about what this means in a moment. The subscript G or U indicates the symmetry property. Okay. Basically indicates the symmetry property with respect to the inversion center of the molecule. Okay. G means is symmetrical, U means is antisymmetrical. Now if you look above the 1s, you find 2s orbitals also interact with each other to produce sigma G and sigma U star as well. Now one thing you notice is that the molecular orbitals produced by 1s is different from those produced by 2s in that the orbital splitting is much smaller in the case of 1s. Why? Because 1s orbitals are much smaller than 2s. The diameter of 1s orbital is much smaller. So they do not have much effective interaction compared to the case of 2s. Okay. All right, going even up, you'll find 2p orbitals interact with each other. Now, there are 3 p orbitals, px, py, and pz. Usually you define the axis of the molecule being the z. Okay, so basically in this case, the 2pz orbital would interact with another 2pz because their symmetry would match each other, and that forms a sigma type of bond. And the symmetry with respect to the inversion center is G, okay, meaning symmetrical. There are 2 other p orbitals. One is px, another is py. The px can interact with the px, and py can interact with the other py. And they basically form two pi bonds in the conventional sense. Okay? And their symmetry property would be both U. Okay? And there's also corresponding anti-bonding orbitals. The anti-bonding orbital produced by the 2pz is sigma u star, and anti-bonding orbital produced by the 2px and 2py are sigma g star, pi g star, and another is also pi g star. Okay. Now we have the molecular orbitals constructed. What we do next is to put the electrons in. Okay? And just a reminder, we put the electrons from fill electrons from bottom to up, and we will maximize maximize electron spin if possible, and we will not put two electrons into the same orbital with the same spin, because in that case those two electrons would have exactly the same set of quantum numbers. Now, if you follow this rule, you will end up with an electron configuration that looks something like this. So you basically fill up all the MOs formed by 1s, 2s, and the bonding MOs of 2p. And finally, there are two electrons left, and there are two pi g star orbitals. So to maximize electron spin, you would put two electrons in parallel and one in each pi g star orbital. All right, now once you have the MO diagram with the electron filled in, we can calculate the so-called bond order, and this basically gives us a rough idea of how many bonds are produced through the interaction of the two atoms. The formula is the following. You take the number of electrons in a bonding orbital, subtract the number of electrons in the anti-bonding orbital, and take the result, divide by 2. Okay, so in the case of oxygen, you'll find that for the bonding orbitals, there are a total of 10 electrons, and for anti-bonding orbitals, there are a total of 6. So the bond order for oxygen molecule is 2. And this is actually consistent with the Lewis star structure. Now, you can make some other predictions. For example, the magnetic properties. In the case of MO diagram, the diagram would predict the oxygen molecule to be so-called paramagnetic, because in this case, there are two unpaired electrons. Now, in those electrons would behave just like small magnets. Okay? So you have unpaired electrons, then you would have a net magnetic spin. Okay? Now, what that implies is O2 molecule would be attracted to strong magnets. A contrast to this prediction is what you would predict from Lewis star structure. In that case, the Lewis star structure predict that the two unpaired electrons in oxygen atom both would form a chemical bond. So those two unpaired electrons in the oxygen atom would be paired with the other two unpaired electrons in another oxygen atom. So there should not be any unpaired electrons in oxygen molecule. Now, this kind of structure would be so-called diamagnetic, meaning that it would be repelled by strong magnets. So this is the case where two bonding theories predict exactly the opposite things, and only one of them would be correct. Okay, so experimentally, it was found that oxygen molecule is indeed paramagnetic. Now, the picture shown here is taken from a screenshot of a YouTube video. The link is provided here. I will also try to insert the link into the on top of the video, so you can just click the link as you watch the video right now. And what is shown here is that there are two steel balls between two strong magnets. There's this milky liquid in between that is liquid oxygen, and this liquid oxygen is actually trapped by the strong magnetic field, and that's a clear indication that oxygen is paramagnetic. Now, if you look at if you watch the video, you'll find there's also experiment done with liquid nitrogen. Liquid nitrogen is diamagnetic. And when the experiment is done with liquid nitrogen, the liquid nitrogen does not get trapped between the magnets. Okay, so this is experimental validation that molecular orbital theory actually is actually a more superior theory than Lewis dot structure, because Lewis dot structure would predict oxygen is diamagnetic, but that's not the case in reality. Now, going back to the theory, in the following slides, I want to briefly discuss a bit of the details of the criteria of forming molecular orbital. The first one is symmetry. At the beginning, I mentioned that to form molecular orbitals, the atomic orbitals must have symmetry matching properties. And this set of cartoon illustrates why that must be the case. Now you look at the top left of this cartoon. It shows two dz square orbitals facing each other end to end. Now this is a case where the two orbitals have exactly the same symmetry properties. And looking at the orbitals, you also realize that these two orbitals can form effective, can have effective interactions, either in a constructive or destructive fashion. In a constructive interaction, the two orbitals wave function add to each other. In a destructive interaction, the two wave functions subtract from one another. And in either way, they can have effective net interaction. Now, if you compare this situation with the one on the top right, this is the case where dyz and dz squared face each other. Now, those two orbitals do not have the same symmetry properties. Okay? For example, if you think about rotational symmetry operation going along the bound axis, okay? Now the dz squared would be symmetrical with respect to that rotation, but dyz will not be symmetrical with respect to that rotation. Okay, so you think about C2, for example. If you do a C2 rotation along the bound axis, the dyz orbital would turn into negative itself, while dz squared would be still itself. Okay, now going back to the interaction. In this case, if you think about the interaction between the two orbitals, you'll realize that because dyz has two lobes facing the dz squared. Now, one lobe is unshaded, the other one is shaded. Now, the dz squared only has one lobe facing dyz, and this lobe of dz squared is unshaded. Okay, so it doesn't matter whether you add these two wave functions or subtract one from another, you always end up with the following situation. That is, there's always some positive or constructive interaction between dyz and dz squared, and there's always a destructive interaction of the same magnitude between dyz and dz squared. So overall, there's basically no interaction at all, okay, because those two interactions will exactly cancel each other. Now, if you look at the other kinds of interactions between the other combinations of d orbitals, you'll find they do share exactly the same kind of pattern, in that if the two d orbitals have the same symmetry property, they can always form effective interact. They can also always have effective interaction for molecular orbitals. And if their symmetry properties do not match each other, their interactions always cancel each other, and their net interaction will be zero. Okay. Another thing about the symmetry is the nature of the molecular orbital that is formed by the interaction of atomic orbitals. And there are three popular common types of molecular orbitals. They are labeled as sigma, pi, and delta. Okay? And those symbols basically indicate how many nodal planes are there um, along the bond axis. Okay? So a sigma bond, you look at a sigma bond, the two sigma bond there. So the sigma bond does not have a nodal plane that contains the bond axis. In contrast, for a pi bond, there is one nodal plane that contains the bond axis. In the delta bond, there are two nodal planes that contains the bond axis, and those two nodal planes are perpendicular to each other. And within each type of bond, there's also this bonding type and anti-bonding type interaction that is also indicated in this cartoon. The next concept I want to talk about is energy, and this energy refers to the energy of the atomic orbitals that makes up the molecular orbital. The key concept here is that if two atomic orbitals having similar energy, then the bonding MO will be substantially stabilized, and the anti-bonding MO will be substantially destabilized. And that will be the scenario of the top of the cartoon. Now, if the two atomic orbitals have very different energies, then the energy gain of the bonding MO and the energy penalty of the anti-bonding MO will be substantially reduced. And if the energy difference is really significant, then essentially the bonding and anti-bonding MO would be the two atomic orbitals themselves. Okay? So in all the cases, you also notice that the bonding MO its energy is close to the atomic orbital that has lower energy. And in fact, it also has more character, so it looks more like the atomic orbital that is closer to its energy. Now, once you understand the requirement of energy and symmetry, we can bring these two things together and talk about how both would impact the construction of molecular orbitals. And this is illustrated in the cartoons here. On the left is the same molecular orbital diagram that I already showed you for O2. Okay? The only exception is that it does not show the MO diagram, MO orbitals produced by the 1s orbitals. So start with 2s and 2p. Okay. Now, this is an interesting situation because there are molecular orbitals having the same symmetry. If you look carefully, there are sigma g orbital produced by 2s, and there are sigma g orbital also produced by 2p, specifically 2pz. Okay. Now, if you think about the requirement, there's symmetry, there's a spatial overlap, and the third one is energy. Okay. Now, this is a case where the two molecular orbitals have the same symmetry. They're both sigma type, and they're both G, meaning that they are symmetrical with respect to the inversion center of the molecule. And they are clearly close to each other in space. Okay. Now, what that means is if their energies are close to each other, then those molecular orbitals actually will also interact with each other, just like two atomic orbitals will do. Okay. And what's that gonna do is they will form two new MOs. Okay. Imagine these two molecular orbitals. they will mix with each other, interact with each other, just like two atomic orbitals will do. And the result is two new molecular orbitals will be produced, and the new bonding MO will be lower, will have its energy lowered, and the new antibonding MO will have its energy a bit increased. And what is the result of that? The result of that essentially is the sigma g orbital produced by the 2s will be pushed down, okay? And the sigma g orbital produced by the 2p will be pushed up. Okay? And this interaction is called mixing. It's called sp mixing, and it will only happen when the energy of the s and p orbitals are close to each other. Now, this kind of interaction basically changes the relative orbital alignment in the MO diagram. In the absence of sp mixing, the sigma g produced by the 2p orbital is lower than the pi u, and in the presence of mixing, the sigma g is higher in energy. Now, it turns out that the relative energy difference between 2p and 2s is a function of nuclear charge. The larger the nuclear charge, the larger the energy difference between 2p and 2s. Okay, so what that means is if you increase the nuclear charge, at a certain point, there will be a transition, okay, from no mixing, from mixing to no mixing. Now, this slide shows the evolution of the MO diagram from lithium-2 all the way to neon-2. Okay? And what you notice is that for low nuclear light elements, lithium-2, beryllium-2, boron-2, carbon-2, up to nitrogen, dinitrogen, the sigma g orbital produced by 2p is always higher, meaning that in those elements, there's always a good and sufficient amount of sp mixing, and that pushes the sigma g level up. For oxygen, for O2, F2, and neon-2, the S and P orbital energy difference is significant, so that there's not enough sp mixing, and in those cases, the sigma g level is lower than the pi u. Okay. So basically, for the second row homonuclear diatomic molecules, there are two kinds of MO diagrams, and their transition is between nitrogen and oxygen. Okay. Oxygen has sigma g lower than pi u, and nitrogen has the opposite. All right. Now, this is the last slide, and basically it shows a heteronuclear diatomic molecule. And this is an example of HF. Now, the diagram here is very similar to the homonuclear diatomic molecule. There are only two things that could be different. One is that the atomic orbitals energy levels are different because, well, they are different atomic species. So even if they are the same kind of orbital, even both are 2p, for example, you cannot draw them at the same level. Okay? Remember, the vertical direction indicates the energy of the orbitals. Okay? So in this case, you have to really look at look up the table of the atomic orbital energy level and decide exactly where you should draw the energy levels relative to each other. Now, in this case, because the energy levels are not as well aligned, you could have s orbital aligned energetically with a p orbital of another atom. Now, what that means is you could end up with orbitals that do not have symmetry matching pairs that are within the ideal energy range to have effective interaction. Okay? And those atomic orbitals will basically not having any other atomic orbital to interact with. So they will become so-called non-bonding orbitals. Their energy, because they will not interact with other atomic orbitals, the molecular orbital they form would be just themselves. Okay, so they will be non-bonding, meaning that their energy is exactly the same as that of atomic orbital. So they do not contribute to bonding. They do not contribute to anti-bonding interaction either. So when you calculate bond order, you just ignore those non-bonding MOs. All right, now this will conclude our video lecture. Now in class, we're going to continue our discussion to talk about heteronuclear MOs. And I will also be posting some exercise about the application of molecular orbital theory in terms of predicting molecular properties. I encourage you to read chapter 5.1 and chapter 5.2 at the very least. And we'll have an in-class quiz on Wednesday, and that will focus on first and second row molecular orbital diagram and its applications. Thank you.